So the goal this afternoon was to have a broader discussion of the problem of decoding. And I thought I'd just make a couple of comments to set that up and suggest taking a step back and again thinking about different approaches we've been talking about this week. And so, at least the way I've been thinking about it, we want a map, one-to-one, isometric, etc., between the two Hilbert spaces. That's really what we're after. And then, of course, we can map the operators to the operators and the evolution to the evolution. And so there have been various approaches to getting information about this map. And one example is this whole discussion of operators, and we've been talking about whether we can really get the good bulk operators from a boundary construction via HKLL, etc., and what the subtleties are with that. But to go back earlier in the week, there's this question of whether we can directly map between the states of the two Hilbert spaces, and in particular, an interesting class of states are the states that are sort of initial or final states for scattering experiments over here. So there was some discussion about that. And it seems to me there are some subtleties. I won't belabor this unless people unless people would like to hear more. But I think this is an important question because this is the question of, when you write down the S matrix, it's a matrix. What are the labels on the matrix? What are the indices describing? And it comes back to sort of Tom's observation. Yes, if we have two Hilbert spaces here, of course you can map one onto the other, but the question is how to map one onto the other in a way that you can usefully identify states in the two theories. You have a description of what your states are doing. So there was that discussion, and then of course there was this whole Mellon story, which I would characterize as the following. Roughly, we can, by some means, extract coupling constants. And, of course, there are questions, are we able to uniquely extract coupling constants of a would-be bulk effective field theory? But, of course, that's not really giving the bulk effective field theory, its Hilbert space, etc. Those are just the couplings, and then really we have to go through the construction of the effective field theory from those constants if we wanted to really take the boundary data and get to the bulk theory. And so that's usually viewed as constructing an effective field theory, but really we know we're not talking about an effective field theory in the bulk. We don't know what we're talking about in the bulk, whatever the correct structure is for string theory, say, and in particular, as we know, we're trying to describe something that, say, gives the right S matrix for gravity. So this seems to be a little bit lacking, at least, it's not clear how to get a full reconstruction via that path, although maybe there will be more discussion on that. So those are just some comments to sort of set up the discussion. Again, we had a lot on the operators yesterday. We could talk more about the whole operator business. I think, Tom, is that mainly your focus today?
No, I have a couple of words to say about it.
More general, okay. And there are these other approaches as well, which we could have more discussion on, or other aspects of this whole question of decoding the whole equation. So, Tom, you want to go ahead? Unless there are other things to bring up.
So I first started thinking about this question of local operators here in Santa Barbara in 1998, and I kind of abandoned it some years afterwards. And I've been trying to remember all the reasons that I abandoned it. Some of the confusions that I had at the time have been cleared up by Dan's work, things having to do with gauge choices and the redundancy, even in ordinary field theory, of local fields versus the scattering matrix. But there were a number of other things that I remembered were bothering me, and these have to do, with respect to this program, these have to do with things that are well known or once were well known in quantum field theory. And they're subtleties in the relationships between operators and boundary correlation functions, or the scattering matrix. And so first let me write down an equation. I think somebody wrote this down. That's not quite the same as what somebody else wrote down. These are called the Yang-Feldman equations. They're written in quantum field theory by writing down the local field equations and then solving them by solving the linear part by a Green's function technique, and then saying that, and I've probably got it exactly wrong, because even though I have a 50% chance of getting it right, I always get it wrong. Saying that if you choose either the retarded or the advanced Green's function here, that you get asymptotically either the incoming or the outgoing field. And this is...
the symbol to the right?
J is the nonlinear source in the field equation.
Yep.
Okay. And this is sort of the analog of what people are trying to do, except, you know, the boundaries look different and the Green's functions look different. And I just wanted to remind you of a couple of remarks about that in ordinary field theory. So first of all, this equation never makes sense as an operator equation. In ordinary massive field theory, it does not make sense as an operator equation in the sense, the equation makes sense, the equation makes perfect sense, but the claim that this field approaches that one at infinity never makes sense unless you do several things. You have to take matrix elements of the equation between in states or out states, and you have to smear the fields by taking their Klein-Gordon overlap with normalizable wave packet solutions of the Klein-Gordon equation that have well-separated support on the boundary. So you have to do both of those things in order for this equation to actually make sense. It's not an operator equation. If you treat it as an operator equation, you come to the conclusion that renormalization constants are equal to 1. This is an old result due to Lehmann, Samancic, and Zimmerman, and they understood all of this stuff back in the 1950s.
It's connected with this whole business.
Sorry?
It's connected with the whole business of getting away the scattering states.
Yeah, right. They defined scattering states by these methods, and they realized that in order to get the proper convergence, even though this equation is true formally as an operator equation, the fields don't actually converge unless you do all of this subtle stuff.
Is this only about UV issues?
No, it's there with the UV cutoff. It's there because the probability of the interacting field to create an asymptotic particle always has to be less than 1 if there's interaction. Okay? And that has nothing to do with UV. Gets mixed up with UV because that Z factor always comes out to be 0 if you take the UV cutoff to infinity. But you put in a cutoff, you have exactly the same problems. Now, once you go to theories with massless particles, this whole thing becomes much, much more complicated. And in the sense of a Hilbert space formulation of it, even for quantum electrodynamics, it was only solved in this obscure paper of Fadeev and Kulish, which there have been. The problem, the infrared problem in electrodynamics was solved in the sense of inclusive cross-sections, where you say, oh, there are all these states of photons that I can't see below some energy cutoff, and I just sum over what they're doing. If you want to talk about exact unitarity, real S-matrix amplitudes, you have to do better than that. Fadeev and Kulish did. They claim to have done the same for gravity. And so those papers exist, but they're extremely subtle. And even in the massive case, all of this stuff is subtle. Yeah?
Does the ADS box help with this? Does it help with these infrared
problems? Let me get to that. I don't really know the answer to that question, but I'm just pointing out things that scared me when I tried to figure out this program.
Is it really true that Fadeev and Kulish solved it? Because I should go back and look. I thought their conclusion was basically that charged particles don't exist.
That's not what their conclusion is. Their conclusion is that the proper definition of states of charged particles always include huge numbers of things that, if you think in Fock space, free particle terms are not single particle states. The actual states are not single particle states.
But what I'm not remembering is whether they actually showed how to create sensitive states to get around.
That's my understanding of their paper.
I mean, this problem exists in any conformal theory as well.
Well, in conformal theories, there is no S matrix in general.
And what is what is the Fadeev-Kulish? I'm trying to remember.
Fadeev-Kulish don't talk about conformal theory.
Well, what do they mean by an S matrix?
They define a space of asymptotic states for QED where, but it's not a conformal field theory.
I understand it's not a conformal field theory. The problem with the conformal field theory is you have this continuum. I don't see how. So Fadeev and Kulish solve the problem better than you can do in conformal field theory.
Yes, that's what I read their papers as saying.
How do they label states?
They label states by a single charge. If the charged particles are massive, they label states by a single charged particle, and then a whole bunch of photons and a coherent Coulomb field. It's a mess. It's not pretty. Okay.
There's countable bases.
Yes.
And what are the labels of that countable basis?
Okay. Now you're asking for details that I don't remember. But there's, it's continuum functions. Continuum functions doesn't mean you don't have a countable basis. You know that. Okay. So I'm pretty sure that it's okay in the QED case. In the gravity case, I would be less sure, but.
Well, if it's true for QED, it's probably true for gravity because, as Weinberg showed.
Yeah. The IR problem is not
it's essentially
any worse. I agree with that.
But Tom, I don't understand what message you want us to take from this.
I don't have any particular message. I told you I'm making random comments about the program that the rest of you are interested in, which made me think that it was not a profitable program to pursue.
So could I make one random comment here as well, which is, I think one could write a similar equation, which would be less helpful for getting the S matrix, okay, but which would be true as an operator equation, where instead of phi in out, you replace that with the limit of the bulk interacting field as you go off to the far future, and then it would be true as an operator equation. That's a random comment.
So what does that mean in ordinary?
What would you mean? Oh.
My point is that it's that latter thing which is more like the program that many of us have been discussing in ADS-CFT, where you try to write the interacting field as some Green's function on the boundary value of the some Green's function acting on the things that come from the actual fully interacting CFT. There's an alternative version of that where you try to replace that free term with the leading term of the 1 over n expansion. And I think that has all the subtleties you just mentioned, and we should be aware of those issues and trying to translate between them. But I think that distinction is already in the discussion, is what I'm saying.
Okay.
Is it something that will only show up at the level of loops in the bulk? Because those haven't been thought about. So is that the issue?
Well, IR problems only show up at the level of loops in the bulk usually. So, but there are subtleties even for massive theories in these definitions of operators and mapping the operator algebra between the bulk and the boundary. Okay.
But at what order do we need to worry about them? Because the IR things are probably less severe because of the ADS.
Look, we know here that at leading order we don't need to worry about anything. And I want to say something about loops, but it's not the order I have things written in, so let me get to that. Okay. All right. So the next thing, this is something Daniel Harlow has been saying every day this week. There are these pictures that Ed Witten drew, okay, that are completely and totally well-defined, okay? They take boundary correlators in Euclidean space, okay? None of these subtleties arise. And he tells you, in principle, order by order in the bulk loop expansion, how you would compute those things given a bulk Lagrangian. And if your bulk Lagrangian is not renormalizable, there will be ambiguities that have to do with what the counter terms are. And there should be, and I believe there will be, if the program that Liam told us about works, which I think it's likely to do, there will be a way of computing those counter terms. Okay? Now, something that confused the hell out of me, again, back in 1998, but was understood, explained to me by various people, some of them in this room back in 1998, that there are two ways in which the loop expansion appears in ADS-CFT. There's a subclass of ADS-CFT models that correspond to weakly coupled string theories. Okay? And in that case, the loop expansion is the 1 over n expansion, and the 1 over n expansion, order by order, has no UV divergences because of string states. States that we can, roughly speaking, think of as things propagating in the bulk space-time like particles. And those are what regulate the UV divergences in loops. In the case of a vast class of other ADS-CFT correspondences, there is no such expansion. Nonetheless, there's still an effective Lagrangian in the bulk, and that effective Lagrangian can be treated semi-classically, and it has loops, and in that case, supposedly, the expansion parameters are kinematic invariance divided by m Planck squared. Okay? And again, there's a question of if I do this, again, starting from the bulk, computing to the boundary, I'm not going to succeed because of loops. There are going to be ambiguities corresponding to renormalization counter terms. And one of the things I'd like to see ADS-CFT do is to compute one of those, okay? And Liam explained to me how he thinks that's going to work. Let's take a very concrete example, ADS-7 cross S4. ADS-7 cross S4, we believe very strongly that there's a low-energy effective field theory. The low-energy effective field theory is 11-dimensional supergravity on ADS-7 cross S4. And let's just think about ADS. Don't take the R goes to infinity limit. R is just very large. And we want to calculate in ADS the Feynman-Witten diagrams for that theory to some order in the momentum over m Planck squared expansion. That should come just from knowing the conformal blocks of the relevant class of low-energy effective operators that correspond to the supergravity multiplet, including the Kaluza-Klein modes. So if we could do the conformal field theory just of those conformal blocks, which should be possible to do at large R because of all of this folklore that's been developed by Peñadones and Joe and so on. That should tell us how to regularize loops in bulk quantum gravity. I'd like to see that calculation done to one loop for a 4-point function, or even for a 3-point functions are not renormalized, I believe, in that theory.
I'm trying to understand that the stuff with Peñadones is only looking at the low energy theory. It's not UV complete. It doesn't know what the counterterms are.
Well, but I'm sorry. I want to extend it by saying all that I'm saying is there's a certain class of operators, and that to all orders in this expansion, that's all I have to look at because all the other operators are up at dimension r squared, or whatever the power is in 11 dimensions. Okay? That should be a well-defined problem in conformal representation theory. Maybe a very hard one because it's in a very high dimension. It's in 6-dimensional CFT. We don't know an awful lot about the representations, but it should have in it an answer to questions about one loop.
So you're not talking about things that cancel just by supersymmetry?
That's right. So I'm talking about things that are renormalized. Okay, so there's some point at which 11-dimensional supergravity needs a counterterm. It's pretty high up and so on, and maybe we want to go to more points and fewer loops or something like that to get.
I think Joe and company showed doing conformal, all this business of conformal field theory will give you the same as effective field theory in the interior. And so you'll have the same ambiguities that you have. You can have the same problem, the same issue that you don't know the counter terms and so on if you did it.
Okay, sorry.
They are not doing the exact bootstrap. They are doing a 1/n expansion of the bootstrap. And what they showed is that the 1/n expansion of the bootstrap is more or less the same as the bulk effective field theory, let's say.
On the other hand, if I asked you to compute, I told you in a certain CFT that all you needed to know was a certain class of operators. And I said I knew the conformal blocks for all of those operators and all their OPE coefficients. This is what Liam just explained this to me the other day, and it sounds plausible to me. I'm not claiming that this is truth.
Well, yeah,
I think this is an interesting program.
If you know all the OPE coefficients, that's more or less the same as knowing the counter term. But I think typically.
Okay. Right. So.
But you are not going to get them by applying the bootstrap perturbative.
Okay. Yes, I agree with that. I'm sorry. Okay. All right.
Are you going to tell us why that's the calculation we should do?
Well, if you
think something might go wrong, or
no, what could go wrong? All the other operators in these theories are up at very high dimension. Okay, it's supposed to be that there's a loop expansion, which is controlled up to counter terms. So you should be able to compute the counter terms.
And what will we learn?
What we'll learn in this theory how UV divergences in quantum gravity in the bulk are regulated by CFT. I think that's interesting.
But that's more or less the same as saying that if you have an effective field theory, and if you know the answer, then you can fix the counter terms. Right?
Yeah, but this CFT gives us another way of knowing the answer if we could compute the correct data of the CFT. Okay, but only in this special limit. So the 1/n expansion of the bootstrap equation is not the right thing, but it is also supposed to be true in these theories that there's a class of low dimension operators. The nature of the loop expansion in these two cases is very different from each other. What's the kind of interesting question here? You might have thought that in quantum gravity that's not in a weakly coupled string regime, that the thing that regulates UV divergences is from the point of view of scattering theory in Minkowski space. When things get too close together at too high an energy, you form a black hole. And I always worried about the possibility that I'd have to understand all of that physics to understand the UV counter terms, Liam is suggesting that's not the case. I think that's an interesting thing to check. Okay.
Are you saying you believe that could, or there's a sensible way that could not be the case, that you don't have to worry about?
This is a semi-other effective theories, let's say for pions, right? All you know is to measure the pion scattering cross-sections, and you can determine the counter terms.
Yeah, that's right. Except here we have a theoretical measurement of the pion scattering cross-section that somebody who's powerful enough might be able to do. Okay. I'm not the person who's going to do it, but I'm just suggesting that it's interesting.
How could you avoid sort of the black hole story if you're really in a very high energy collision?
Your intuition about that is exactly the same as mine.
Maybe
but Liam, well, it's very similar to mine from that point of view. Liam suggested another route. I think it's interesting. I told you, I'm just making random remarks here. There's no coherent story. These are things that, okay.
Can I just make a little comment on that?
Yeah.
I mean, there might actually be a classical version of the answer to the question Steve's asking. Because, I mean, it comes up in numerical relativity, too. Like, if you collide two black holes, you don't really need to know and keep track of a lot of the details of the physics close to the black holes when they're merging, because the actual horizon of the merged black hole is going to end up being further out. So if all you're looking at is the physics outside that comes out of the collision, you can actually completely ignore, because of causality, a lot of details. Now, if you're talking about a very high energy quantum collision, I mean, at some level, causality is still playing a role, and maybe, the details are masked in the coefficient of the higher dimension.
So what if it decays? Right. The black hole. It doesn't classically.
But he's asking about the effective field theory.
Yeah. Let me be a little bit more precise. If I think in the ADS context, okay, at least the large black holes are things that I have to think about in terms of very high dimension operators. I said something stupid about that the last time I was in this room talking, but the Kyriakos reminded me how silly I was being. It's very high dimension operators. There are a lot of them. They have a very closely spaced spectrum, but they're way up at high dimension. And so that would say that there's a massive breakdown of this program of getting Witten diagrams out of conformal field theories that have low dimension operators with a gap. Okay? If that were true, there's a technical problem. You need all of the high dimension operators if black holes are somehow relevant to regulating these divergences. Liam's suggestion is that that's not true. I think it's very interesting to work on that. It seems like a problem that's within the realm of things we could actually think about doing. That's the point I'm trying to make, and thank you for posing it in a way that sort of made me not stumble over what I was trying to say. Okay. The final thing that I want to say about this whole business is, there's a minor thing. Let me just say it because a lot of people won't know it. There's a connection between the Feynman diagram picture and these kinds of equations. That was something that was worked out many years ago. After all, this gives you a connection between phi in and phi out. Dyson worked it out. There's this terrible set of formulas with something he calls double graphs with both retarded and advanced propagators, and you solve it all, and you find the usual formula for the S matrix in terms of time-ordered Green's functions. It's an absolute mess in field theory, even though we know how to do everything, to really go from these equations to these answers. Okay? There's another way, which Feynman discovered and Dyson turned into operator formulas, and you just don't use these equations to do it. So possibly another lesson. But now I want to talk about something else, which is this R goes to infinity gives Minkowski space thing, which Joe and Lenny Susskind suggested many years ago. And I believe it's right, but I think it's important to understand how it's right and how non-uniform the limit is. And so the point is that how big R has to be is really very, very process dependent. Even for very, very low energy processes, if the total energy is large enough. So if you have a low energy scattering where all the little sub-energies are very small, but there are lots and lots of particles in it such that you start to create black holes, then the limit is extremely non-uniform. The simplest example is let's put in enough energy that what I'm going to do and direct it at the right time in the right place so that I form a large black hole, okay, in anti-de Sitter space. That state doesn't have an R goes to infinity limit in Minkowski space. There is no such stable equilibrium state of the theory. We cannot describe that scattering amplitude by taking the R goes to infinity limit. So now let's think about small black holes, because after all, we're not really interested in just calculating graviton scattering amplitudes at low energy. We can do that in effective field theory, modulo a few constants if we really wanted incredible precision. We're really interested in what happens when we create black holes. So if I create a small black hole in anti-de Sitter space, it decays. And what does it decay into? It decays into the anti-de Sitter gas. Okay? Now, if that decay occurs on a time scale short compared to the anti-de Sitter radius, then that decay will hit the boundary more or less untouched. Okay? The decaying stuff won't get a chance to equilibrate and form the ADS gas until much, much, much later. So for that black hole scattering amplitude, everything is okay. But that means that the lifetime of the black hole, the page time of the black hole at which I can expect to get out all the information, has to be short compared to the anti-de Sitter radius if there's any hope that I'm going to extract that scattering amplitude from the ADS correlators. Now, on the other hand, if I'm thinking about graviton scattering, I don't want to look at ADS correlators over times that are that long, okay? Because then I start to get things bouncing back and forth between the walls because the particles get out very quickly. So the limit by which ADS goes to flat space exists, but it's very non-uniform in the process. It's not an operator kind of limit. It's something that depends on which matrix element, which process you're talking about, how you take the limit, how much bigger R has to be than the system that you're forming. And these things are things that, again, indicate to me that thinking about local fields in anti-de Sitter space in this operator fashion is sort of not the right way to be attacking the problems that we really want to study. The problems we really want to study, which have to do with black holes primarily, have to do with all of these states that we cannot describe in terms of low energy particles in anti-de Sitter space. The ones we know are there because of the Hawking-Page transition. And so far, the best description I've heard of them in the gauge theory is kind of explicit, not just saying, oh, there's this huge set of high dimension operators that have a very closely spaced spectrum, is Eva's description on the Coulomb branch, and the extent to which that can actually be worked out is something that I think is really interesting to think about. It doesn't have a nice set of formulae in terms of boundary operators. Okay? Those operators, there are W boson operators, but they're incredibly, at weak coupling, you can write them down. They're incredibly complicated functions of the bulk gauge fields and so on. And you just would not want to think about them in the conformal field theory. They make sense on the Coulomb branch. They don't make sense when you take the limit to the origin. Okay, that's about all I had to say. And I'm sorry it was so random, but these are just the thoughts that came up while I was watching other people's talks.
Other comments or questions for Tom?
Put the microphone up here. There's fair game for anybody.
Why don't you, go ahead. You want to put the mic?
Well, it's better if they're not recorded.
They will be. We'll just have to work hard to hear it.
He's a much more cautious.
Yeah, so these are some comments that came up last night at dinner, so perhaps. This business of bulk reconstruction, so it's based on precursors, right? So precursor is something which, some operator which is local at some time, and then it evolves into the interior to become something in the interior. And some of the problems in this construction have to do with things that never get close to the boundary. So they are deep in the interior and never get near the boundary. And so somehow, and this is purely a bulk issue, that we are trying to describe a bulk operator here by waiting till it gets close to the boundary, and then we pick it up near the boundary, we understand the dictionary, and then we go back into the interior. And there are, so I think we really should think about more generally as trying to reconstruct a bulk operator as some kind of non-local operator on the boundary, and even for cases where maybe it never becomes very small. So, so one concrete example where you have something in the bulk that never becomes very small is in the case that you have, so there are some examples of gauge theories, so SUN super young males at level K, some theory like this.
Again, when you say never becomes small, it's on the boundary.
Yeah, they never get to the boundary. Yeah, so people discussed examples. So yesterday there was a long discussion about the Rindler idea situation, or there are situations with black holes, and yeah, Vladimir and Dan Gavat were explaining to me various other cases where you have very massive objects, and you cannot get out. So one example is there are some theories of this kind in 2+1, which are confined, so there is a boundary, right? And then there is some interior, so this is R equals to 0, so completely small. And in some situations, these theories have a low energy as a Chern-Simons description, a purely Chern-Simons description. And in the bulk, that occurs as an extra brain that you put here, so this is an D brain, with a Chern-Simons gauge field. And if you put this whole construction, this whole theory on, let's say, T2, then there will be Wilson lines of this Chern-Simons theory. In the bulk, they correspond to, again, Wilson lines here. And these are operators that definitely are not local. So they never get them from something that is close to the boundary, and then, so they're really not local on the boundary. They are Wilson lines on the boundary. But while in the interior, again, they are things somehow trapped to these brains in the interior. Now, okay, so that's some random comment. So we'll, yeah.
So what? If you did something much simpler of taking, say, two two precursors that would have been individually localized but at different times, there would also be the bill of never being sort of simultaneously out on the boundary.
Yes, yes, but well, the way that things were constructed is that you construct them individually and then you superpose them, so that would not pose a problem for any of the constructions that have been discussed.
So, I'm sorry, there's a gravity joule to the term science theory of KITP.
So this is a completely well-defined example where you can find the literature and so on.
So did it matter that it's a Chern-Simons theory on the
What?
Can you say again why it mattered that it was a Chern-Simons theory on that?
Yeah, so what I wanted was a situation where you had, well, first of all, it's some degree of freedom on this D brain.
Right, which could be, there are many ways that can happen.
There are many ways, yes, but it's definitely non-local in the bulk. So it, well, once you are in the T2, it's some Wilson line on this D brain. Right.
I mean, the D brain itself is localized and never is at the boundary.
It's localized in the bulk, right?
Yes.
It's deep in the interior.
Yes.
You cannot measure it by doing something here. Well, you can insert the Wilson line here.
Mm-hmm.
And so yeah, that way you could measure it, but it's clear in the description that it's well, always deep in the interior. It's not something associated to a particle that is moving and sometimes could be near the boundary or it has some wave function.
I understand. I'm just saying you could always do that with a D brain. I don't understand where the Chern-Simons matter.
Oh, the Chern-Simons is a mechanism to generate observables that are Wilson lines, which are topologically non-trivial. They are manifestly non-local in the boundary theory. So these Wilson lines cannot be measured by local operators. It's only by non-local.
That's fine.
Well, I don't know. I intended to bring clarity.
So, one, at finite string coupling, why is the D brain any different than a star or a planet in the interior?
No, not different. Yeah, not different. That's why I'm saying this is an example.
Okay. But then at finite string coupling, the D brain has the same probability to fluctuate out to the boundary, if you will, as a star or a planet. I mean, it can reach the boundary. It's not. I mean, at small g, it's nailed down.
Especially when I compactify. Yeah, that's true. That's in that sense it is.
Yeah.
But if the point is that something getting close to the boundary is some object that has some small probability of becoming small. Right? But maybe there might be objects that never somehow become small, or they have very low probability of becoming small. They have exponentially suppressed probability of becoming small, and those were the ones that were causing problems before. And maybe we need a construction that constructs this as well-known local operators.
Well, small may not be the right word. I mean, we talked about yesterday. You know, if you could have a surface operator or a volume operator that covers the entire boundary, produces some D brain localized to the boundary. That's something which is at the boundary, but it's not small physically. It's just high energy.
Yes.
I mean, it's a little harder for this route D brain to get out to the boundary than an isolated star because the energy density gets the warp factors of the warp factor, but
only a little. Or some piece of it.
It's wrapped on something that's proper size going to infinity as you go to the boundary.
Some piece of it has a probability to fluctuate out to the boundary, even if the whole thing has a hard time getting out there.
Yeah, but there's a penalty for that as well.
Yeah, it's a little harder. It's like a star.
It's a gigantic gradient.
It's a star that's tethered in the bulk. I mean, it's got strings. It's got stuff attached to it.
You're saying in this case, you know what the precursor is, right? You're saying all you're doing is putting a Wilson line on this brain, and you know which operator knows about this. It's just a Wilson line in the boundary theory. And then this thing that was brought up yesterday about things commuting is the point that this Wilson line in the boundary theory should be somehow smeared over time or something?
Doesn't the dual geometry have a null singularity?
In this case, well, I picked a case where this was a confining theory, and then you, for one particular value of k, and then it's a confining theory, and then you change them slightly, and then you get the next one.
I see. So
then it's, I mean, it still has a mass gap, but it has this topological and non-trivial degrees of freedom. But these are small details, but maybe not important. Then there is a kind of toy model of a situation like this in matrix quantum mechanics that might be useful for thinking about this. I'm not sure whether it's useful or not. Maybe it's too trivial. So single matrix quantum mechanics contains well, the usual reaction m dot square plus b of m, right? So first we can start, and then the point is that if you look at the gauge invariant subsector, you have a system of n-free fermions. So this is a situation where, for let's say quadratic potential, you would fill the Fermi sea, right? And you have so initially this is a system in 0 plus 1, but there is an emergent spatial direction, which is the surface of this Fermi sea, and you have the particles, the fields moving here. In the analogy, I think we should think of the boundary as somehow living here, so this would be like the boundary, so the region where the Fermi sea is deepest. And then what we are trying to do is, in the usual reconstruction, is to try to, so we insert some field operators for the bulk field. So there's a bulk scalar massless field at this position, and then the natural evolution somehow brings it back and forth to the interior. And then from inserting this at different times, we get this operator in the interior at different positions. And the difficulties that were discussed were analogous in this toy model to considering a situation where we have a more complicated potential, where deep in the interior you have second region. And so if you sit here in the boundary, you have a little bit of a hard time sending the signal here. There is the potential barrier. But in this situation, so using the free fermion description and the density of fermions and so on, we have a more direct way of constructing the operator, so an alternative way, if you wish, because we can explicitly solve it. And we see that a more efficient way is not to think about this, try to solve the equation in time direction, but to somehow directly construct the bulk and being able to construct the operator a little more directly. And probably we might need something of this kind to overcome these difficulties. That was one point. Second point I wanted to make is related to the tensor networks, and it's the one aspect of it. So which is an aspect that, well, I'm not sure. Maybe it's obvious to most of you. So when you construct a tensor network, so you could view the construction as a unitary operation, which so normally when people write so the point is that people normally describe these tensor networks as a sequence of unitary operators. And when you think about it this way, so this is manifestly a unitary operator, but here they sometimes add qubits in the vacuum, and then it produces the state in the far future. And so in each time you have a 3-point vertex, you have a qubit in the vacuum, and well, the final qubit at the very bottom is also in the vacuum. So the network gives you a way to start with the decoupled states and then building up the non-trivial interacting state of the theory. And so the question is, so this looks a little bit more like de Sitter than anti-de Sitter. So it looks more, this type of structure is precisely the way we construct the quantum state at late times in de Sitter. So each time we evolve, we get the space gets bigger, the relevant space gets bigger. And there are modes that come from the Planck scale, which are analogous to these guys, but they come in the vacuum. So they come in the vacuum, the space expands, and then they interact perhaps with the neighbors, and then they continue to expand. And this way we build the state of the system. Okay, so that's one remark. And the question is, how is this connected with the discussion in anti-de Sitter? So one way this seems to be connected is that you could take, let's say you're interested in the state at t equal to 0, right? So that's the state that on this time slice, and you can construct it by, well, people normally draw the tensor network as existing somehow in this time slice. But well, with tensor networks, the modes are not clear, so I can draw whatever picture I want. So instead of thinking about that, let's think about the deceit. So let's think about, let's take t equal to 0 and view how we can build the state at t equal to 0 in a way that mimics the de Sitter evolution. Well, we can certainly choose here the Sitter coordinates, right? Mm-hmm. So on the boundary, we choose a conformal factor so that this piece of the cylinder, so it's a piece of the cylinder, which has global de Sitter space.
So you're not going all the way to minus infinity?
No, not the way to minus infinity, so we're imagining, so here, this is the neck of the de Sitter space. Of course, we could do this in the planar description. It's a little, we could also do it, and then we get the state at t equal to 0. And then we go all the way to infinity, so it's a little more well, that would be closer to this picture. So maybe we could just say that. So we start at t equal to 0, let me modify what I was saying. And then we go into the past, but using the de Sitter metric. And in that way, we naturally get this structure. So we get exactly this structure, and we can think of this tensor network as being prepared by the field theory itself, the field theory now in the Sitter space. So
you want to think of states as not being created by some Euclidean path integral, but by real Lorentzian evolution
exactly,
on Scrap class.
Yeah, so one issue is that, well, people who do tensor networks, they like to think of these things as unitaries. And so I asked some of the experts, why, because if you view the tensor network as describing a slice of space, there is no obvious reason for choosing them to be unitary. So I asked them why they chose them to be unitary. And what they said is that it was for convenience, because if you evaluate an operator, correlation function of two operators here,
it seems to
then
be
you take psi square and you average, only this piece of the network is important. So of course you could say the same words in the Sitter. So in that case it was for convenience. Another reason is that you could create the state in a quantum. So once you find the network this way, you could actually create the state in a quantum computer, for example. So that's another response that I've heard from this question.
So how much of the symmetry of the de Sitter is reflected in the tensor network?
So tensor network preserves a discrete subgroup of the symmetry group. So if we are doing a 1D CFT, the full symmetry group is SL2R squared, right? And the tensor network is discrete subgroup gamma within one SL2R, some diagonal SL2R. Which is there's just the symmetry of the Escher picture.
Is there a characteristic scale built in this tensor network?
No.
And if you cut it
it's
off,
a basic ideas, yeah.
if you cut it off at a finite time, it's not a subgroup anymore.
No, that's the symmetry of the infinite. No. Yeah, so the remark was only intended to say that there is a natural choice of coordinates, a natural way to think about the field theory, which looks essentially where the time evolution in those coordinates looks exactly like built in this tensor network description of the state. That was one remark.
So this is also slightly non-standard from the usual way we think about de Sitter, because the Scrap class is now in a conformal frame where Scrap class is hyperbolic space. Right? It's not a sphere.
The de Sitter is actually in the boundary. So let me be more precise. So we have a field theory, let's say in R4, right? So these are the four-dimensional coordinates. So this is R4. One of the coordinates is time, so let's say df squared plus dx squared, right? Yeah. It's R3. And now all we do is we just choose a different conformal frame. So now this is the Sitter 4, right? So here at the bottom we think of it as the Sitter 4, and it's preparing the wave function at t equal to 0. So that's one particular way of preparing the wave function, which manifestly has the description of the tensor network. So of course, here you have all these various de Sitter slices. Well, you could even add the extra leg that puts extra information that the happy people were having, and that corresponds to adding extra operators in various locations.
Can you actually do this in higher dimensions? Or?
Yeah, this is true in any dimension.
This is true.
I use the conformal symmetry.
Sorry, I'm confused. So that picture initially was supposed to be a slice in the bulk, but now your decider is the
But this
putting the
shows why
network
it is
on
so
just on the
flexible. So
boundary.
now we have it slicing. Now we have it realized as time evolution in the boundary theory.
Just in the boundary.
Yeah.
So there is, so far there was
Yes,
nothing
yes.
that would have gotten you.
There is nothing, yeah. So we could think of the tensor network as being space-like. We could think of it as being the time-like evolution. And I think we could also probably think of it as being there's another natural thing to think about this, which is, so we want the state here, right? And we could think of a null surface that comes out here, right? And this has the feature that it's, well, neither time-like or space-like. And maybe the tensor network somehow describes the state somehow on this null surface. So the fact that, for example, if you have extra legs coming in carrying some information, the fact that the area has to increase, well, we know there is the Busso bound and so on that tells us that the area has to increase if there is entropy coming in.
So you could make a tensor network with unitary evolution that reproduces all sorts of FRW spacetimes if you wanted to, right? This isn't.
Oh yeah. This is not particular to.
When you said you know how to do it for higher dimensional CFT, do you mean like sort of very roughly in principle, or can you say what operators to place at the vertices of the network to create, let's say, the ground state of n equals 4 super Yang-Mills theory?
This is basically n equal to 4. The n equal to 4 super Yang-Mills at specific, in the sitter. So you take a Hubble volume, you take the field theory in a Hubble volume regularized with a cutoff shorter than the Hubble volume, and that's the Hilbert space that's appearing here. I mean, it's the Hamiltonian of the theory, the unitary operation that takes us from the initial states to the final state. So the initial states, some of the initial states are the UV modes that then get at energies below the cutoff. Right?
Yeah,
that's what this is representing. Yeah.
That's the easy part, I think. But then when you inject new vacuum, you have to actually entangle it with the pre-existing state in the appropriate way to actually grow the vacuum.
Sure. This is what this step is doing. And then this step is, this step is entangling it with the neighbors.
Right, but do you know what operator to write down to implement that entangling? Because that's the dynamics of the field theory.
Yeah, that's the dynamics of it. I'm not solving the field theory. I'm just saying if you could solve the field theory, you could do this. For free field theories, we know how to do this. For any equal to 4, we just do exactly the same thing. Well, it would be the problem would be more complicated. If you had a computer, you could do this. It's not something that I think it's fine. It's a well-defined problem. We just cannot do it.
Oh, that's funny. I've wondered about exactly this. Whether how obvious is it that the state, since you're doing something discrete, but you're trying to generate a state that at long distances looks like the vacuum with no spurious excitations due to the thing that's you're doing wrong at the discreteness scale.
Yes.
Is it that clear that you really will? And since you're doing it forever, it's not like you did it in the distant past and any mistakes were washed away. It's like you keep doing it as you keep growing the vacuum. So how do you know that there isn't a kind of permanent error that's built up in the UV and that you don't really generate the continuum vacuum state this way?
I don't really know whether it's how difficult it is to do it in practice. If you had the theory, but it sounds like something that you should be able to do.
So if I gave you the list of operators and operator dimensions and OBE coefficients of n equals 4, do you have sort of an idea of what program we would give to the computer to implement?
No, I wouldn't know how to do that from that point of view. So for the computer here, you would give them the Lagrangian, just the usual Lagrangian.
Okay, so the weakly coupled theory, you would know how to do that.
Yeah.
Because we know how to do
Or the strongly coupled theory, you just give them the strongly coupled theory. And they would do this.
So I should mention, you can extract, I mean, you can sort of go the other way. You can extract like 3-point functions and read off, operator, product, expansion, and things. I think if you have the network, you can do all this stuff. But going backwards, I don't think. It seems like in principle it could be done.
Yeah, you could then do all these things. But
yeah, right. But it seems in principle, I don't know. There's a concrete problem of inverting that map, and I don't know if people have done that yet.
Going from the operators to the state.
Yeah, if somebody if you solve the field theory to build
this is a microscopic description of the states in terms of the original variables.
Yeah.
It seems like there's an important difference between whether the tensor network is space-like or is time-like tensor network on the boundary from the perspective of reconstructing the bulk operators.
Yes.
Right, like in the picture where it's space-like, you think the operator at the center is really just the bulk operator in the center.
Yeah.
And you don't need to do any other funny business.
Yeah.
Whereas here you might think that the operators along the tensor network, you then need to use some of the smearing functions or something still to get the actual operators.
Yeah, I agree.
Do you think, do you have anything to...
I don't have anything to add. I don't have anything to add to this discussion. Only trivial comments that, in this description, the operator at the center is something that you insert very early on here. Some operators which are further away the level of pictures is the same picture. It is really, we should do better than the level of pictures.
So you had suggested that maybe there's a hope of making a nice compromise by taking this null surface.
Yeah, so we don't know what it's. Yeah, space-like is what everyone normally says, and I like the space-like. It's not that it's nice for the Ruta-Kayanagi prescription and so on. This time-like thing is something that naturally tells you what these tensors could be. That gives you an actual construction of the tensors. Finally, this null thing is, I think, nice from the point of view of the Busso bound. So if you think about it this way, it both gives you a rationale for why they should be unitary, and also a rationale for, this business, it's a nice set of surfaces that has figured out before and might be useful.
Except that for generic state, that's the sort of nastiest surface because it has all these sort of crossover seams and whatnot. Yes. So it's not as, but whereas the other cases where you
that might be
nice
that might be a good way not to think about this.
But I don't know.
There's another set of null surfaces in anti-de Sitter space, which I think is, for me anyway, more clearly one where you try to implement the Busso bound. Namely, if you go to the FRW coordinates,
yes,
and you take the diamonds that have to do with a finite proper time in the FRW coordinates, between the two periods of the song.
Yeah, so the FRW coordinates live inside here, right?
Right.
And then I think if you understand correctly, you get these diamonds, and you take the surface further and further out.
I don't think I've understood the point about the Busso bound here. Are you saying that the Busso bound is like this entropy bound on the tensor network if we think about the tensor network as being on the null surface?
Yeah, so if we think of the tensor network being on the null surface, and so here we've always we always thought about tensor networks which are where you have these zero states, so things are always growing, right? But you could have situations where it stops growing and it more or less stays always with unitaries without extra zeros. But if you had extra information coming in from in the bulk, right? So this qubit could be entangled with something else outside the system, right? That is coming in the bulk. And so the idea is that we will need to grow this network in order to be able to accommodate those, because we have the things that are unitarily evolving, and then we have extra legs coming in, and we need to grow the number of legs. This is all pictures, it's not.
In this picture where you're doing the de Sitter evolution on the boundary,
yeah,
what's better about making it discrete and calling it a tensor network than just doing, Hamiltonian evolution and the de Sitter coordinates on the boundary?
Nothing. We just showed, if you're only interested in doing the Sitter and preparing the state, nothing. I was just trying to connect this tensor network discussion to something we already know about the zeta space. Trying to, well, hopefully makes its tensor networks more concrete for it. I mean, it gives you...
But with this discrete version, maybe help us go into the bulk, because the discrete version is like a, a regulated boundary and then
well, I think
a regulated de Sitter boundary kind of.
Well, as Douglas was asking, I mean, we have all these possible slices in the interior, in time lag, and so on, and we really should understand what the time direction in the bulk means and how to choose different time slices. I don't have an answer to that.
So, I'm sorry. Suppose we're doing this in free field theory.
Yeah.
When you say you're putting a single state in here each time, I'm not sure I completely understand what you're. So there's some degrees of freedom that haven't been included yet, and you're putting states of those in such that you end up with the Bunch-Davies vacuum, right? Mm-hmm. So, but is that something that I can think of as just one state of the theory of the new degree of freedom entangled with everything else?
Yes. So this is the fact that in the Bunch-Davies state, the modes that come from the UV come in the vacuum, right? So it's a full harmonic oscillator. This is a harmonic oscillator degree of freedom that we put in the vacuum.
So coming in means coming in the sense you're breaking it up into free modes.
Yeah.
And come in just means that KH equals 1.
That's the standard. I mean, this is I think.
No, I was thinking of sort of local fields.
No, but well, you do have degrees of freedom. The degrees of freedom passing the cutoff. So you have.
Yes,
that's what
this is. So these guys have the degrees of freedom coming in from that had energy above the cutoff, and then they now have energy below the cutoff.
Those are simple in momentum space.
Yeah.
And they're non-local in space. Whereas your network, I think I understood it to be a kind of local thing in space.
It's the same confusion.
Yes. But
this is exactly the problem I've been wondering about for years and trying to figure out, can you grow it in a way that you get the Bunch-Davies vacuum? It just seems not clear even for a free field theory.
Well, maybe I'm too naive, but I would choose Hubble patches, right? So each region is a Hubble-sized patch, and you choose some cut of epsilon, much more than the Hubble patch, right? And you keep that fixed. So the next e-fold, you have e more of this. Well, let's say we have two-fold that we duplicate the number of Hubble patches, right? So we have more modes in here than we have here. Right? Mm-hmm. We're just saying that we.
Well, it is true that like you would reproduce the right correlators for like a massless field in de Sitter using some kind of dumb stochastic evolution is maybe a classical version of this, but I think also in the quantum problem it should work. But I certainly know in the classical problem some stochastic version like this will give you the right long-range correlations, from some discrete model like that.
But only if you work in momentum space.
No, in position space, just random walks in position space. Every Hubble time, the field takes one step. This is kind of the quantum version of that.
Well, I think Ted wants to build, a physical lattice, right?
Well, whatever it is, I have to know at the end of the network, if you're telling me that the density of nodes is 1 per Hubble volume, then I haven't really constructed the local vacuum.
But it's 1 over epsilon, the d per Hubble volume. But each square here represents a Hubble volume with a lot of degrees of freedom, right? 1 over epsilon to the d.
Oh, so you're injecting not sort of a single degrees of freedom at the cutoff, but the entire.
It's not a qubit. It's a huge number.
It's a collection of qubits in sort of one state.
Exactly.
Yeah. Okay, that's
it's
what.
All the ones that are coming in from.
Okay, that I think I understand.
Good.
I have nothing more to say.
It's almost cookie time. Anything else pressing people would like to raise? Then let's adjourn for cookie. All right.